Hello everyone, myself Dr. Santimay Kundu. I welcome you all to the fifth lecture of soft computing techniques. So, we have covered fuzzy sets and membership functions, basic operations and their properties, graphical representations of union, intersection, etc. So, there are few more algebraic operations. So let's start with the algebraic product of two fuzzy sets. So let A is a fuzzy set. We are writing that the fuzzy set A, the first one is that algebraic product of two fuzzy sets. So algebraic product of two fuzzy sets, let there are two fuzzy set. One is that A equal to x mu ax. X belongs to the universe set X. Then another fuzzy set B, which is x mu bx. X belongs to capital X. So the algebraic product of these two fuzzy sets can be written as A into B, which is that x mu ax into mu bx. X belongs to the capital X. So this is known as the algebraic product of two fuzzy sets, which is denoted as A dot B, and this is defined as that. So let's one example where Ax equal to, you can take any fuzzy set. Let A is a fuzzy set which is equal to, the order pair A is x, x2 0.4, x3 0.6, x4 0.8. B the fuzzy set which is x1 0.1, x2 0.3, x3 0.5, x4 0.7. So A into B, the algebraic product of these two fuzzy sets A into B is x1 0.02, x2 0.12, x3 0.3, x4 0.56. So this is the algebraic product of two fuzzy sets A and B. Now we are going to learn the multiplication of a fuzzy set by a Cripps number. So we are considering a fuzzy set A. So let's define only A. A is the fuzzy set x mu x, x belongs to x. So let a number, let alpha is a Cripps number. So let alpha be a Cripps number. So multiplication of a fuzzy set A by the Cripps number alpha is known as alpha A, alpha dot A. So it can be written as the fuzzy set x alpha into mu ax, where this x belongs to the universe set X. So here we are take the example, let's take the same example, x which is equal to x1 0.2, x2 0.4, x3 0.6, x4 0.8. So that is the fuzzy set A. Okay, so this is the fuzzy set A. So now let alpha equal to 0.04. So alpha equal to 0.4. So this alpha is a Cripps number, is belongs to 0 to 1. So alpha belongs to 0 to 1. So let alpha equal to 0.4. So here we can write the alpha A, alpha into A, which is equal to x1 0.08, x2 0.16, x3 0.24 and x4 0.32. So this is the multiplication of a fuzzy set by a Krebs number. Similarly, B and then try to find alpha B for some number. Now, power of a fuzzy set. So A is a fuzzy set. X mu Ax, X belongs to that universe of discourse, that is X. So power of a fuzzy set, so you can write that a to the power p, a to the power p. So a to the power p can be written as that x mu Ax whole to the power p. So this is the order pair, and then this is called the power of a fuzzy set p. So if greater than equal to 1, then ap, the power of the fuzzy set p, so a to the power p is called concentration, is called concentration, is called concentration. If p is less than 1, then a to the power p is called dilation. Okay, so let the same example, we are writing that a equal to the fuzzy set x1 0.2, x2 0.4, x3 0.6, x4 0.8. Let p equal to 2, so it gives the concentration. So a to the power 2, or you can write a to the power 2, you can write it like x1 0.2 to the power 2, 0.2 whole square, so that is 0.04. You can write it x2 equal to 0.16, x3 0.36, x4 you can write it 0.64. So that is called the power of a fuzzy set. Next is that the algebraic sum of two fuzzy sets. So we are assuming two fuzzy sets A and B. So let A is a fuzzy set which is X, same set X mu X. X belongs to capital X, which is the universe set of discourse. So and B is a fuzzy set which is that X mu Bx, X belongs to capital X. So now the algebraic sum of these two fuzzy sets you can denote as A plus B, which is X mu A plus B X. X belongs to the capital X, where mu A plus Bx given as mu Ax plus mu Bx minus mu Ax mu Bx. So that is the algebraic sum of two fuzzy sets. Let's take the same example. So let's take the example for same set. So A equal to x1 0.2, x2 0.4, x3 0.6, x4 0.8. B is x1 0.1, x2 0.3, x3 0.5, x5 0.7. So here A plus B the algebraic sum of the fuzzy sets A and B is equal to x1. Now 0.2 plus 0.1, that will be 0.3 minus 0.02, so you will get 0.28. So x1 0.2, next 0.2 you will get 0.58. 0.58. So let's take the example 4, 5, so that is 0.7 minus 0.12, so 0.58. Now x3, and so for x3 0.6, so it is 1.1 minus 0.30, so then 0.5 minus 56, so you will get 94. This is x4, so you will get x4. This is x4, so you will get x4 0.94. So this is the algebraic sum of two fuzzy sets A and B. So simple, mu A plus Bx is mu Ax plus mu Bx minus mu x into mu Bx. Now bounded sum of these two fuzzy sets. Okay, bounded sum. So here we are writing the same fuzzy set A and B. So bounded sum fuzzy set A, which is x mu Ax, x belongs to A, B x mu Bx, x belongs to x. So bounded sum we can write like A, B. So give a bound like it's denoted as bounded sum of two fuzzy sets. So this can be written as x mu, write like that, A, B, x, A, B, x. So x belongs to this x. So where mu A, B, x is defined as minimum of 1 or mu Ax plus mu Bx. So first we add the membership function, membership value of the each element A plus B. We will take the minimum with 1. The minimum of 1 and mu X plus mu Bx. So let x1 0.2, x2 0.4, x3 0.6, x4 0.8. For all the examples we take the same value of A and B. So x1 0.1, x2 0.3, x3 0.5, x4 0.7. So now denoted bounded sum. So here x1. See, if we add it, we will get 0.3, and the minimum value of 1 and 0.3 is 0.3. So that is 0.3. Now x2, minimum value of 1 and 0.7 is 0.7. So x2 0.7. Now minimum value of 0.6 plus 0.5, that is 1.1, and with 1 minimum value is 1. So x3 1. And also 1.5 the sum of mu A and mu B. So minimum value 1 and 1.5 is 1. So for x4 we will also get 1. So this is known as the bounded sum of two fuzzy sets. Once again I am saying that this different notation for in some different book. So that is the notation. So notation may vary. Okay. Now the algebraic difference of two fuzzy sets. So one fuzzy set is A. Same example. The fuzzy set B, the same example. So algebraic difference can denote as A minus B. So that is the fuzzy set x mu a minus bx, x belongs to the universe of discourse x. So okay, so that is the where defined as where mu a minus b x is that mu a intersection b complement x. So that is known as algebraic difference of two fuzzy sets. Okay, so let there one example. We are taking the same set A, which is x1 0.2, x2 0.4, x3 0.6, x4 0.8. B, we can take x1 0.1, x2 0.3, x3 0.5, x5 0.7. So B complement, you can write it B complement x1 0.9, x2 0.7, x3 0.5, this is x4 0.3. So that is A, B and B complement. Now A minus B. So A minus B is x1. The intersection of the set A will take the minimum value. So 0.2 and 0.9, minimum is 0.2. For x2 0.4 and 0.7, minimum value is 0.4. For x3 minimum value of 0.6 and 0.5 is 0.5. Then 0.8 and 0.3, 0.3. So x4 0.3. So this is basically gives the algebraic difference of A and B. The algebraic difference of two fuzzy sets A and B. Next is that the disjunctive sum of two fuzzy sets. So two fuzzy sets we are defined as A equal to the fuzzy set X mu X, X belongs to X, B X mu Bx, X belongs to A. So the disjunctive sum, here the notation is A plus B. A intersection B complement union A complement intersection B. So the disjunctive set is denoted like that. So let's consider one example to how to find the disjunctive sum of two fuzzy sets A and B. So here A, we are taking the same values x1 0.2, x2 0.4, x3 0.6, x4 0.8. B, take x1 0.1, x2 0.3, x3 0.5, x4 0.7. So take A complement, which is x1 0.8, x2 0.6, x3 0.4, x4 0.2. Take B complement, which is x1 0.9, x2 0.7, x3 0.5, x4 0.3. So we have calculated A, B, A complement, B complement. Where A, B given in the questions, A intersection B complement. So the minimum value of A and B complement. So first and last, take these two. So minimum value x1 is 0.2, x2 is 0.4, x3 is 0.5, x4 is 0.3. So minimum value of A and B complement. Okay. So now take A complement and B. So the minimum value is x1. So take these two. x1 0.1, x2 0.3, x3 0.5. Then you can take x4 is 0.2. So A complement, no? So A complement x3 is 0.4. So once again check 0.9, 0.1 is the value which is basically 0.1, 0.8, 0.1, 0.6, 0.3, 0.5, 0.4 and 0.2. x4 is 0.2. Now take the union. So if you take the union, so that is the value. I am going to write that value here, disjointing sum. So answer A plus B. You will get it x1 0.2, you will get x2 0.4 maximum value, x3 0.5 and x4 0.3. So that is the minimum value. Okay. So for this example, disjointing sum of two fuzzy sets. You will consider any two fuzzy sets and try to find the disjointing sums. Now, terms. First one is having distance. Let A is a fuzzy set. So A is x mu x, x belongs to x. B is a fuzzy set, x mu b x, x belongs to x. Let these two sets have n elements. Now the having distance is denoted as DAB and it is defined as summation I equal to 1 to n xi belongs to x, that the numerical value of the difference of these two membership function, that is mu x and mu bx. So we'll take the numerical value, that's taken as mod. So this is known as the having distance of two fuzzy sets A and B. Now it's one example. So as we are taking A equal to x1 0.2, x2 0.4, x3 0.6, x4 0.8, B equal to x1 0.1, x2 0.3, x3 0.5, x4 0.7. So the having distance between these two fuzzy sets, we can write the difference of that. So magnitude of 0.2 minus 0.1 plus mod of 0.4 minus 0.3 plus mod of 0.6 minus 0.5 plus mod of 0.8 minus 0.7 7. So you will get 0.1, 0.01, 0.1 plus 0.1, so that is 0.4. Okay, having distance can be defined between these two fuzzy sets. Now next one is the Euclidean distance. So let here also the A is a fuzzy set x, b, x mu x, b fuzzy set x mu x, so that also have n elements. So Euclidean distance between these two fuzzy sets can be written as EAB square root of summation I equal to 1 to n xi belongs to x mu a xi minus mu b xi is whole square. So that is known as the Euclidean distance. So that is a equal to x1 0.2, x2 0.4, x3 0.5, x4 x3 0.6, x4 0.8, b x1 0.1, x2 0.3, x3 0.5, x4 0.7. So equivalent distance of these two fuzzy sets EAB can be calculated as EAB equal to square root of 0.2 minus 0.1 whole square plus 0.4 minus 0.3 whole square plus 0.6 minus 0.5 whole square plus 0.8 minus 0.7 whole square. So that is basically 0.1 whole square, so that is 0.01 plus 0.01 plus 0.01 plus 0.01, which is square root of 0.04 can be written as 0.2. So we define the Hamming distance and Euclidean distance of two fuzzy sets A and B. So conclusion. So in this class we have learned the algebraic sum, we have learned algebraic product, bounded sum, power of a fuzzy set, and two more terms, which is Hamming distance and Euclidean distance. Question is that assume any two fuzzy sets and calculate all these terms what we have learned in this class. Calculate algebraic sum, product, bounded sum, algebraic product, bounded sum, and Euclidean distance. So solve these questions. So these are the reference of today's class. Thank you.